Okay, lesson 25. This is the last problem in section 9 point, what was it, 7? Yeah, 9.7, Taylor polynomials. Problem number 8 asks us to find the third Taylor polynomial for sine of x, expanded about c equals pi over 6. Regretfully, this is not nice for us, but it will work. Okay. What we're going to do here then is we're going to start out with, we know f of x is equal to the sine of x, and I want the third polynomial. So I'm going to write down here, I want p sub 3 of x. Okay, that's what I want. Well, for me to find that, okay, I need what is, and I'm going to go ahead and look at my my notes right here. Okay. This is going to be f of c, the first value, plus the first derivative at c divided by 1 factorial, times x minus c, okay, plus the second derivative at c divided by 2 factorial, times x minus c squared. Again, this is the 0th, first, second, so the third degree would be the third derivative at c divided by 3 factorial times x minus c to the power of 3. I hope at this point of the notes you are 100% comfortable with memorizing where the Taylor polynomial comes from and that pattern. Okay. Now, I have been flying through these in the videos. This is the thing to know. If I ask you anything about Taylor polynomial, it doesn't require any real knowledge. It's just plugging things in, evaluating what we need, and plugging things in. Now, I want to approximate this function at the value of c equals pi over 6. Okay, so what I'm going to do is I'm going to go ahead and take the derivatives. I need the first, the second, and the third derivative. So f prime of x is cosine of x, the second derivative is a negative sine, and the third derivative is a negative cosine of x. Next thing I'm going to do is I'm going to plug in the c value. So f of c is going to be sine of pi over 6. Now, it's been a while. We're going to go ahead and look at pi over 6 being this point here. I know that the sine values increase. So this is 1/2, then radical 2 over 2, then radical 3 over 2. Pi over 6 is the smaller angle. So that means that sine of pi over 6 is a 1/2. First derivative of c is going to be the cosine of that value. Well, cosines decrease, so it's radical 3 over 2 and then increasing in the unit circle. So this is radical 3 over 2. Then I have negative of sine of x. So the second derivative at c is going to be a negative 1/2. And the third derivative at c is actually going to be a negative radical 3 over 2. Okay. All I did was I plugged in pi over 6 for all of these values to get all these values. I now know what this is, this is, and this is. Okay. I also know that c in all these must be replaced with pi over 6. And honestly, once I do all that, I'm done. So the third degree the third degree Taylor polynomial is f of c, which is 1/2. Plus radical 3 over 2 times 1 over 1 factorial times x minus pi over 6. Okay, this comes to 1/2. This whole thing rewritten down here. Now, I rewrote f prime of c as radical 3 over 2, and then I wrote this as 1 divided by 1 factorial, and then this piece by itself. Okay, I'm going to do the same thing for all these. So the second derivative of c is going to be the negative 1/2, so I have negative 1/2 times 1 over 2 factorial times this thing, this x minus pi over 6 to the power of 2. Okay, and lastly, plus negative radical 3 over 2 for this top piece, negative radical 3 over 2 for that top piece, times 1 over 3 factorial, times an x minus a pi over 6 to the power of 3. Again, in other classes, you might be forced to simplify this entire thing down. In my class, honestly, you did the calculus necessary. As of right now, leave it like it is. Okay? And actually, the pattern will be more visible in the long run if I start slowly manipulating this, not doing everything. Okay? So, with all these problems done, you'll read number 9 in our notes. In most Calc 2 classes, you'd come across an accuracy, an approximation. How good is this approximating polynomial? Okay, we are not going to do that in this class. Okay, it's a very, very difficult thing to do. Okay, it's very similar to the Calc 1 topic that we used before when we tried to approximate whether or not or how accurate a linear approximation was. Okay, just keep in mind that all these approximating polynomials that we're finding, they are approximations. Okay, they're approximations. They're not perfect, but they give us a good idea, okay, as to where we can guarantee the graph being appropriate up to a certain point. Okay, that's all I'm going to have to say about the Taylor polynomials right now. Keep in mind, okay, that the Taylor polynomial is specifically just a formula, and we have to make sure we fill it in very carefully and very appropriately. Okay. That concludes the notes for section 9.7, lesson 20.